Thank you for joining me again with Alpha Beta Ratio Made Easy. Just to stress on the fact that you may not be able to understand this lecture except after looking back to lecture Alpha Beta Ratio Part 1 and Part 2, because it was like a step-by-step understanding of the Alpha Beta Ratio. Also, I have to stress on the fact that this is a very simplified explanation of the alpha beta ratio. If you want to go into more and more depths, I would like you to refer back to the piece of our paper published by Professor Jack Fowler with the 7th step to heaven, understanding the alpha beta ratio. And I think it's free access online if you want to have a look at it. Before starting with this lecture part 3, and in this part we'll have to go ahead and do some calculations of the dose equivalency. I had a very interesting question actually regarding breast cancer patient, and the question is saying, look, Dr. Haddad, you're talking about the late effect using high dose per fraction, and nowadays after the publication of the long-term effect of the START trial, we are using 2.67 gray, or the total dose of 40.05 gray over 15 fractions in breast cancer patients. So why we are doing that, although we do care about our breast cancer patient, the cosmetic outcome on the long term with fibrotic changes is very important, and is something that is of really great concern in any radiation, for any radiation oncologist. And the question can be answered simply by telling you that there is two major factors affecting the late effect in our radiotherapy treatment. One is the dose per fraction, and the second is the total dose we are giving. And if you want to have a very interesting lecture, or if you want to hear a very interesting lecture about the radiobiological background of the breast START trial, I would like to suggest for you the lecture given by Professor Arnold. He is one of the pioneers of breast cancer, and he was one of the first author, as I can remember. I can't remember if he was the first or maybe the last author for the START trial. And he made a very clear statement, and when they started to do the START trial, they were trying to find which dose should they use. And if you stay with me, and we may do some dose calculation to see how much of the 40 over 15 will be equal to how much in the regular fractionation or the normal fractionation, we will see together that 40 in 15 is almost equal to 45 gray, and it's not equal to 50 in 25, meaning that if you compare 50 over 25, which is a conventional fractionation for breast cancer, when you compare it to 40 in 15, we know that 40 and 15 is less hotter, meaning that it's not equivalent to 50, it's less than 50. And when we look at the long-term results, the 10-year survival, there was no difference in local tumor control, as well as no difference in the cosmetic outcome. So if you can save your patient 2 weeks of extra time of treatment, so why not to do that? But you have to understand, we didn't use 2.67 and give a full dose equivalent to the 50 gray, but we gave a smaller dose in total, which compensated for the late effect. And this was one of the beauty of the START trial, and I hope this will answer the question. Let's go ahead and start using the equations now, because this is the most important part of the lecture. When we look at the dose, when I tell you I'm giving 50 gray, this 50 gray is an absolute dose, and it's not reflecting the effect of the dose on the tissues we are exposing it to the radiation. For example, if I'm giving 50 gray, if I'm giving this 50 gray in 10 gray per fractions over 5 fractions, it would be the same as if I'm giving the 50 gray over 25 fractions? Definitely not. If I'm giving this 50 gray to the spinal cord, will the effect be the same as the oral mucosa? Definitely not. And this is why we needed an equation that will allow us to compare different doses, but at the same time on different tissues with different fractionation. So we need something to allow us, to give us an idea about what kind of dose, but taking into consideration the effect on which tissue we are giving this dose, and this effective dose, or this is the biological effective dose, or the BED, is an expression of the dose in terms of tissue and effect. And if you look at the component of the biological effective dose, or what we call it the BED, what kind of factors, what's the factors that you may be able to imagine to be part of this equation? Definitely it will be the total dose. I mean, how much you are giving in such a particular tissue. Is it 50 gray? Is it 60 gray? Is it 70 gray? So the total dose should be part of the component of this equation. And that's why you can see here in the equation that there is the ND. N is the number of fractions, as you can see here, and D is the dose per fraction. And I would like you to keep it like that, because it will allow you to change the D and N separately. If you want to just put here the total dose, that's also fine. Multiplied by 1 plus D over the alpha beta ratio. 1 is a factor, and if you want to know exactly how we created this equation, I would like you again to refer back to the paper that we just mentioned at the beginning for Professor Jack Fowler and 7 Steps to Heaven. This ND will be multiplied by 1 plus D is a dose per fraction, very similar to that, over the alpha beta ratio. And the alpha beta ratio here is, it depends on the tissues you are irradiating. For example, if you want to compare two regimen over a certain type of tissue, you have to know what's the alpha beta ratio of this particular tissue. And as we said in the previous lecture, we divided our tissue into 2 major categories. We said that the late responding tissue, we will give them alpha beta ratio of, yes, exactly 3, and we also said that the tissues with rapidly proliferating tissue, or rapidly responding or acute responding tissue or early responding tissue, we will give them the value of 10. So alpha beta ratio will change depending on which tissue and which tissue is receiving that dose. And this is a very important equation. You have to know it by heart. Again, BED equal to the total dose ND multiplied by, open parenthesis, is 1 plus D over the alpha beta ratio. The biologically effective dose is, as you can see here, there is another biological factor in the equation, and that's why they call it the biological effective dose. We are looking on the actual effect, putting into consideration the tissue we are irradiating. Again, repeat with me, ND or the BED equal to ND plus 1 plus D over the alpha beta ratio. You have to repeat it and repeat it and repeat it till you put it in your mind. You have to know it by heart, please. This equation, there is 2 equations that we will have to remember today, and there is no excuse not to know it, and it's a very simple equation. If you understand the component, you just put the component in your mind, total dose here, dose per fraction here and there, and the alpha beta ratio is there, and ND multiplied by, open the parenthesis, 1 plus D over the alpha beta ratio. Let's use this biological effective dose to compare two different schedules together. By the way, this part of the equation called the relative effectiveness or the relative effective dose multiplied by the total dose will give us biological effective dose. This is a very practical example. This was an EORTC trial in head and neck cancer, and there was two arms in this trial. One arm, they used 35 fraction, 2 gray per fraction, which will give us a total dose of 70 gray. And the second, I'm sorry, the second schedule or the second fractionation, they used hyperfractionation 1.15 gray twice daily for 7 weeks, and the total number of fractions was 70 fractions. The total dose here will be 80.5 gray. So they wanted to see if there is any benefit from hyperfractionation over conventional fractionation. Important point is to keep apart 6 hours apart, so maybe a session early in the morning and early and late in the evening. Let's look at the biological effective dose for the first regime and for the second regime or the second fractionation. We are not expecting that 30 gray in 2 gray per fraction, 35 fractions in 2 gray per fraction will be equal to 70 fractions with 1.15 gray twice daily fractions. So let's try to compare these two fractionation schedules and see which of which is hotter, which of which is cooler. But before we go through that, you have to ask your question. You want to see, or you want to compare the biological effective dose of two fractionation schedules on which particular tissues, because if you are calculating the BED for the late reacting tissue, for example spinal cord, it will not be the same as you are calculating the BED for the early responding tissue or the rapidly responding tissue, as for example the tumor. If you know, the alpha beta ratio undifferentiated squamous cell carcinoma is around 15. Alpha beta ratio for the tumor in head and neck cancer may reach up to 15, so it's very high. But for simplicity, we usually use again the 10. Look at the first fractionation schedule, the BED. But when we are looking here on the late effect, so when I say the late effect, your alpha beta ratio will be 3. Yeah, you can take 3 or 2, that's fine, but you have to let us know which alpha beta ratio you used it in your equation. Again, put the equation and you have to write it several times so that you remember it. ND is the total dose multiplied plus 1 plus D over the alpha beta ratio equal to what? ND will be equal to 70 gray, which is 70 here you can see. 1 plus D, D is a dose per fraction for the normal fractionation, which is 2 gray per fraction. And the alpha beta ratio here is 3, so 1 plus 2 over 3, and this will be equal to 116.7 or 117 gray. And to let us know that this is not an absolute dose, this is a biological effective dose, you have to write it like this, gray, and I use the alpha beta ratio of 3, so I'm putting it gray 3. For the second fractionation, let's see what we have. For the second fractionation, a BED for the second fractionation, again over the spinal cord of the late effect. Total dose is 80.5. If you multiplied 1.15 times 70, it will give you 80.5, and 1 is the same plus 1.15, which is the dose per fraction, and alpha beta ratio again should be the same as we used before, because we are looking for the late effect. We are putting the alpha beta ratio of 3, and this is equal to 111.4. Please let me know if you didn't get these results, and maybe I did something wrong. I have to revise it, but I think I did it long time ago and I didn't revise since that time. For the early effect, including the tumor, because the tumor is a rapidly responding tissue, so we are rapidly proliferating tissue, sorry, and I would expect the alpha beta ratio to be very high, maybe 10 plus, but for simplicity we are going to use the alpha beta ratio of 10. We can again put the ND as 70, This time we'll use D as 2 gray because this is a conventional fractionation method, and the alpha beta ratio at that time will be 10. Repeating the same equation again for the second, sorry, this BD for the second, I'm sorry that it's 1, should be 2. For the second fractionation schedule, it will be 89.8. So this is the results of the equations, but how we interpret these results? Look at the first part. Here we are looking at the spinal cord or fibrotic changes that may affect our patients. If you looked at this first fractionation, our dose was equivalent to 116. The biological effective dose is 116.7 gray 3. For the second fractionation regime, it was 111, meaning that for the late effect as an endpoint over the spinal cord, for example, our hyperfractionation is even cooler on the spinal cord when you compare it to the conventional fractionation. And if you go back to our curve, or our cell survival curve, I told you that the late reacting tissue with small dose per fraction can tolerate the dose better. And you can see here in terms of the alpha beta ratio is 3, you can see that our late effect with the fractionation of 1.15, reducing the dose per fraction, even if it's twice a day, still it's cooler on the spinal cord, as you can see here. For the rapidly proliferating tissue, including the mucosa, including the tumor itself, you can see that hyperfractionation is hotter again on the tumor. If you looked at the results of the trial, of the EORTC trial at that time, they will tell you that local tumor control was better for the hyperfractionation. And you can see, because that the total or the biological effective dose is hotter on the tumor, we did expect something like that. So local tumor control was better for the hyperfractionation, but they will tell you also that mucositis was again worse for the hyperfractionation because the mucositis is because the mucositis will be affected very similar way to the tumor or the early reacting tissue. And now you can understand how we are playing with it. A third schedule that we can also put, this is what we call the simultaneous integrated boost, and in exactly the same way you put the total dose, you put the dose per fraction, you put the alpha beta ratio for the late reacting tissue, and then you get up the number. You have to repeat the dose again with alpha beta ratio of 10 for the same fractionation scheme. And from this equation, again, the biological effective dose compared to the conventional fractionation, you can see that over the late effect is less than 116, the result that we got it in the previous slide. So it's less hot on the spinal cord, and if you look on the tumor itself, it's more or less very comparable, if not hotter a little bit. And so you can do it for any schedule you want to compare. For example, 20 in 5 versus 30 in 10. You can compare 30 in 10 versus 30 in 15, and you can get the biological effective dose for the first and biological effective dose for the second schedule or fractionation, and you compare it over the normal late reacting tissue and the normal rapidly proliferating tissue as well as the tumor, and then you put the figures in front of each other and you compare both together. But this is a very tedious process, and in the daily practice you may need something quicker. And here comes the second equation that you have to know it by heart. And saying that you have to know it by heart, so let's look together on one of the most important equations in radiobiology, where you can compare two schedules or two fractionation schedules together at the same time, and you end up by an equivalent dose rather than you calculate a biological effective dose into 4 equations, or you can reduce it to be only 2 equations. Let's look at the, please try to remember it by heart, and it's very important to understand the major component. The equation will take two schedules at the same time. So there will be one schedule with abnormal fractionation, and this will be D capital nu, which is the total dose using any abnormal fractionation, any fractionation other than 2 gray per fraction. And D capital ref is the total dose with the normal fractionation of 2 gray per fraction. So D capital ref is any total dose you are gonna give the patient with 2 gray per fraction, will equal to alpha beta ratio, and this can be changed depending whether we are dealing with the late tumor effect, late radiotherapy effect, late reacting tissue, or tumor or early or rapidly proliferating tissue. You can change the alpha beta by, you can put it 3, you can put it 10, depending on the type of tissue you are comparing two schedules on which tissue we are dealing with. And D small ref is a dose per fraction, and you can simply remove the D small ref and put 2 because it's 2 gray per fraction. This is the conventional fractionation. This is the reference fractionation dose, so we can put it as 2, and this will simplify the equation even further. And it is divided by alpha beta ratio plus D small nu, and D small nu is a dose per fraction with any abnormal fractionation. Again, D capital nu over D capital ref equal alpha beta ratio plus D small ref over alpha beta ratio plus D small nu. Again, D capital nu over D capital ref equal alpha beta ratio plus D small ref over alpha beta ratio plus D small nu. If you try to remember it like that, making a song, making whatever way you want to write it down, please make emotions on it as much as you can. As Jim Quick was telling us, if you link emotion to the information you are trying to remember, you will end up by this information to be a long-term memory. And sometimes we, in our lectures with my colleagues, we just make a song from this equation so that we remember and we laugh together. But at the end of the day, we go out of the lecture and we do remember it, and we can use it on daily practice. Please, when you try to put D nu, because sometimes it's very confusing, the D capital nu should be opposite to the D small nu, and the D capital ref should be opposite to the D small ref, because sometimes you put it up and down and you change this arrangement, then you end up by different or wrong results. So D capital nu over D capital ref equal to alpha beta ratio plus D small ref over alpha beta ratio plus D small nu. I'm sorry, there is two equal sign here. There should be no sign here, just it's an one equal sign, but please make sure that you are multiplying this part by this and multiplying this by this. So now from this equation you can see easily that you can get the D ref if you have the rest of the information. You can get the D capital nu if you have the rest of the information. So, but when do we usually do that? I would say that usually we do use, or we search for D capital nu when we are looking, for example, to hypofractionation. And for example, you are now very close to the Christmas time, and you want to make your patient finish before Christmas time. So you want to hypofractionate your schedule. For example, he has 5 remaining sessions and they should be taken over 5 days, and you want to give it over 3 days. So 10 gray over 2 gray per fraction, with 2 gray per fraction, how much of those should I give to finish my treatment in 3 days? 10 divided by 3 days, so you can calculate the D small nu, and then you will get up the D capital nu from this equation. But don't be confused now. Let's go and do some examples to explain this further. Let's look at the STAR trial, because this was a question at the beginning of the lecture. In the STAR trial, we used 40.05 gray in 15 fractions. So if I'm trying to try to see that 40 gray per fraction in 15 fraction will be equal to how much dose if I'm giving 2 gray per fraction, which means that now I have an abnormal fractionation. So 40.05 is the D capital nu, which is the total dose using a fractionation that is different from the 2 gray per fraction. So D capital nu will be 40.05 gray. D capital reference, this is what I want. I want to see how much the 40 in 15 will be equal to, if I'm using a 2 gray per fraction, how much equivalent dose will be. So D ref capital, this is what I want. Alpha beta ratio will depend on which tissue you're looking for. Are you looking for the fibroblast or you're looking for the breast cancer? See that breast cancer alpha beta ratio is not that high, by the way. It's between maybe 3, 4, and so it's very close to the late late effect tissue or the late reacting tissue. The DREF, we said that DREF is a dose with conventional fractionation, so this should be 2 gray. This is without saying, and we'll divide it by alpha beta ratio. It should be the same. If you choose 3, then it will be 3. If we're looking for the late effect, we're looking for late reacting tissue. And D small nu is the dose per fraction using the abnormal fractionation. And 40 in 15 means that the D small nu will be 2.67 gray. Let's calculate this and see how much the 40 in 15 will be equal to. If you multiplied it, so the D capital ref will be equal to 45.4 gray. And this is what we said in the beginning, by the way. I told you that the 45 in 15 is not equal to 50 gray in 2 gray per fraction, not equivalent. And that's why, so we reduce the total dose. Instead of giving a dose that is equal to the 50 in 25, we gave a dose that is less than the 50 in 25. We ended up by very similar local tumor control, and also we ended up by the same cosmetic outcome. We didn't have any long-term side effects in terms of fibrotic changes or cosmetic appearance or chest wall fibrosis and things like that. So this is the beauty of the radiobiology. This is the beauty of the equations, and you can. So now we know that, yeah, now we have, if you want to give an equivalent dose, you can give 43 gray, 4 gray per fraction, and you can divide over the days. You may end up by 3 weeks treatment, something like that, maybe less than that, 40, I think it's 2 weeks treatment, something like that. So it's very simple and very simple way of doing things. So just to summarize what we said now, we have 2 equations. One equation is the BED, and you will use both, by the way. BED is very important, and you cannot forget about it. For example, I'll give you an example. We are treating spinal cord re-irradiation. For example, we say for re-irradiation of the spinal cord, just keep the BED to be 130 and 140 BED gray 3 dose. And then you may need to calculate the BED for the dose you give it to the patient before. For example, you give your patient in head and neck, and the spinal cord received 50 gray or less. Very important point when you are trying to calculate any dose for re-irradiation, you have to be sure how much dose this structure received. For example, the spinal cord, if you are giving 2 parallel opposing fields, or you're giving IMRT, or you're giving conformal, the spinal cord is not necessary to receive the full dose, by the way. So if you're giving, for example, tumor of 60 gray, this doesn't mean that the spinal cord was treated by 60 gray. You have to go back to your plan. Look at the spinal cord dose. Look which ice dose line was, and the spinal cord was on it. For example, the spinal cord received 40 gray, but 40 gray in total, the number of fractions was 30, for example, which means that the dose per fraction for the spinal cord, I'm not talking about the tumor, but for the spinal cord, which is your concern in pre-irradiation, was less than 2 gray per fraction, means that there may be a room for the spinal cord to have more fractions, because if you miscalculated or you calculated the dose given by that structure in the wrong way, you will end up by under-treating your patient. So this is a very important point. You have to put it into consideration. The second equation is a very practical equation that you can use it in daily practice. And I will give you an example right away. And please bring a piece of paper and a pen and do this example with me. If I'm asking you that your radiographer or the physicist just called you on an urgent basis saying, "Doctor, please help me, help me." So you say, "What happened? What happened?" And he'll tell you, "Your patient, you prescribed 50 gray in 25 fractions, 2 gray per fraction for your breast cancer patient. Unfortunately, what happened was that your breast cancer patient was treated 3 fractions with wrong dose, and they are really scared and they don't know what to do. So they came to you and they're asking you, what can we do now? What can we do?" So you just tell them, "Calm down and tell me what happened exactly. Let's calculate it using our equation. Write down with me D capital nu over D capital ref equal to alpha beta ratio plus D small ref," that's what we called it, remove it and put 2 gray or 2, over alpha beta ratio plus D small nu. Back to the equation that we previously we wrote it down, and then try to analyze what we have now. The patient received a wrong dose. She received the first 3 fractions. Instead of 2 gray per fraction, she received 5 gray per fraction. So this means that she received the 3 fractions times 5 gray. This means that she received now 15 gray. 3 times 5 equal 15. So this is a total dose with an abnormal fractionation of 3, meaning that the D capital nu here, if you are following me, will be 15. And I hope you are all agreed with that. So the total dose given with the abnormal fractionation, which was an irradiation accident, of 5 gray per fraction. It's an example, by the way. You can do whatever you want to do and change it. And then D capital ref, this is what I want. Why this is what I want? Because I want to see the 15 gray per fraction on my tissue, which is, for example, the fibroblast. The 15 gray per fraction over the fibroblast is equal to how much gray or how many grays if I'm giving my dose by 2 gray per fraction, which means that the D capital ref is a question mark. D small nu is the dose per fraction using the abnormal fractionation. In our case or accident now, we used the 5 gray per fraction. D small ref again is the 2 gray per fraction. So can you please do it with me? Now we have to multiply and we have to solve our equation, and D ref will be equal to 15. Yes, are you following me? So why 15? Because it's D capital nu, and times D small nu here will be 5, and the alpha beta ratio we are looking for the fibroblast will be 3 over the dose per fraction with the normal fractionation is 2 plus again 3, meaning that D capital ref will be equal to 15 times 8 over 5. If you remove the 5 with the 15, then you end up by 24 gray. So the 15 gray in 3 fractions that the patient had by accident will equal to 24 gray in total. So you may say that Okay, I originally prescribed 50 gray, and now by accident she received 24 gray, then the remaining dose is 21 gray, and you can divide 21 gray over 2 gray per fraction. You may end up by 11 or 10 sessions left for your patient. So you can see how efficient, how quick you can do the equation. Please, if you try to repeat it and repeat it, you will never regret that you hear this lecture. You feel that you are dealing with radiation accidents, biological effective dose, the re-irradiation in a very, very good way. Please remember the equation, try to remember it by heart, put it in your heart, put it in your mind, and try to repeat and repeat the equation, and try to do several examples so that you end up by using the equation. And if you need anything, please don't hesitate to contact me on the website or my email address Mustafa.Haddad is HADDAD at Qasr Al Aini, as you can see it in the first slide, .edu.eg, and I'm happy to answer any question and to get in touch with you. Thank you for following me, and wait for further lectures, and thank you very much. Take care.